Hello everyone, and welcome to this meeting of the Warren Astronomical Society. I'm the president, Bob Tremblay. Do we have any first-time attendees tonight? We do have. Hi there, how'd you hear about us?
Hey, Charlie.
You did. Awesome. Thanks, Charlie. All right.
We get a bonus for referral?
I'm proud to refer.
You know what? Let's bring that up at the next board meeting. That's a fine idea. Okay, as a general tradition, we like to do a roll call, go through the ranks, and state your name. So I'm going to flip this around. I'm Bob Tremblay, president, and you guys see who's talking. So yes,
Mish.
Bernie Mish.
Third meeting.
David Bransky, treasurer.
Tina Wong, card carrying member.
Sonny Spilos, average member.
Mike Dollar.
Laura.
Tom Thurgonet.
Pete Lemire.
Charles Strackbine.
Kelsey.
okay. I still haven't figured out a way to go in order online, but we have Kelly PD, say hi, and we have Bob Berta, and we have our speaker. Now, how do you say your name? I don't want to get it wrong when I announce you tonight.
It's Rajib Ganguly.
Okay. And we have Kenneth. Okay, so viewing audience. There we go. Hey, I actually did the viewing audience. If anyone wants a lanyard, which I can't find my SSA badge or my lanyard. It was put in a very safe place, and then the basement got cleaned. So yeah, so I'll find it. So let's see. Big announcement: astronomy at the beach tomorrow and Saturday night at Mayberry State Park, west of Northville. I plan to be there manning or crewing the WAS table. If you have any freebies, if you'd like to show up, great. If you have any freebies you want to pass out, bring them, because I'm all out of Solar System Ambassador freebies. Gave them all away at the eclipse. Let's see. And tell everyone you know about it. It's again Mayberry State Park, and I'll put the link up in chat, and we'll talk about it a little more later. WAS Wearables, if you want to purchase a t-shirt or something like that, take a look at our newsletter and see what's there. Mark Kedzier back there can take an order for you. WAS elections are next Cranbrook meeting, so that is in 2 weeks. If you would like to take one of the positions on our board, I believe they're talking to you, aren't they, Mark? Yes, so talk to Mark Kedzier. That's November. That's not October. Okay, November. Thank you. Getting my months messed up. Okay, GLAC meetings. The Astronomy at the Beach event is put on by the Great Lakes Association of Astronomy Clubs. They meet every second Monday of the month. If you're interested in helping put the event on, we'd love your help. We can get you on the mailing list, and you can join their Zoom meetings. There's also a mailing list, glaac.groups.io, and you can get all of the email from GLAC and see what's going on with them. WAS calendars. Dale Teamy has put in a Herculean effort. There is a huge email chain going on about the problems with printing prices and stuff like that. Chances are the calendar is going to be a little more expensive this year. Sorry. Not much we can do about that. Still waiting on board approval for the count. Dale says 40 or 50. Do we have any left? When did we run out those things? Was it in June?
I think I gave a couple away about the June or July.
All right, we got to get Dale Teamy or Dale Parton how many we need. Okay, let's see. Officer reports, astronomy at the beach. Biggest event of the year. We're all gonna be there. Dale Parton can't be, our first VP cannot be here tonight. He's taking his 95-year-old mother to her high school reunion in Toledo. Wow. So go mom.
That's awesome.
That is pretty awesome. He's always looking for short and long presentations. So if you have a 15-minute or a 1 hour long presentation, get with Dale, and he'll gladly schedule you for next year. Riyadh, is Riyadh online? No, he's not. So the picnic was really good. The star party after the picnic was really good. And we're going to be having another event, fourth Saturday of the month. So let's see. Treasure, David, any news?
Okay, so currently as of today, in our checking account, we had $24,650. In PayPal, we had 401.67. And I think we got an insurance bill that's due coming up due
Yep.
next month. So it's about 1,000 something out of there, but we're still flush with cash.
And you gave me the check for our club,
Check for
the Glatt Club tables. So I'm going to be taking that in my laptop bag out and giving it to them tomorrow.
if
Okay, Charlie.
anybody's interested in being treasurer. It comes with a really neat briefcase. You get a really neat checkbook. And if anybody wants to buy a dome, you get to use this.
Does it have chairs?
Yeah. Got checks.
Charlie,
I'm Charlie Strackbein, and I'm the secretary of this fine organization. And I have to say that our newsletter was published on the first of the month, and excuse me,
Yeah.
beautiful, right? And I do have to report I bought a C-Star S50 entry level astrophotography smart telescope. And I've been having a lot of fun with that. And I encourage anybody that's entry level, want to learn a lot, to look into that.
All right, thanks, Charlie. And if you're going to be at Astronomy at the Beach, there's a pretty sure bet you're going to be seeing a couple of those out on the field, and one of those is the grand prize for the raffle. So that is very cool. I will probably be putting in for the raffle this time. Let's see. Outreach. Jeff McLeod is not here, but Jeff McLeod is getting our giant Dobsonian telescope out at Astronomy at the Beach, and he's going to be there with his Gemini simulator. So it's going to be a great event.
Yeah.
Yes.
We have the Dob, if your big Dob is loaded, if there's anybody who wants to learn how to operate the Dob at the Chinese Beach, come see me. Give you some quick lessons.
All right, Marquez here again, repeating, if anybody, we're going to be using our big Dob there, and if you'd like to learn how to use it and show the public some of the wonders of the sky, he will gladly show you how to use that. You showed some people how to use that at the picnic, didn't you? Or somebody did. They set it up. I know somebody was.
Last year, Chalia learned how to do it, so she took it over for about an hour.
Well, how long is the line for that television? Isn't it always like a
200 feet.
Oh my God. So we need to come up with something to do with the people in line. Like I a couple of years ago at a Perseus event at Stargate, I had my giant meteorite and I was just talking to people up. I'm at the table. I can't do that. So if anybody has an idea what to do with 200 people doing this, waiting for a telescope, maybe
Encourage them to join, and they can watch online.
yeah, you would. Go up and talk to people. That would be awesome. We go first to do that. That would be fantastic. So let's see. Publications. Vichalia is not here, but our newsletter is up. Our award-winning newsletter with our award-winning newsletter editor, Dale Teamy. Stargate Committee. Anything yet? Not yet. Or do you have something? We have a subcommittee who is taking a look at how to spend some of our enormous amount of money on upgrading our observatory or getting another building like a warming room, that kind of thing.
What I said in the email thread was that we are going to meet as a board and start to define further what we want to do, because we've been going back and forth between improving the one that we have or perhaps building a new one. But then it was brought up that the light pollution might not be a good site to even invest in a new one. We might want to look at a different site to invest in a new one. We're gonna do that.
50 years ago, there wasn't any light pollution problem there. Oh,
Well,
well.
that was the last thing we talked about, and we can bring that back up with the board.
Yeah, we have a board meeting on the 30th. So if anybody wants to attend the board meetings online, I should really send that out to the membership. I'll make sure I do that next time at the board meeting. You just see what we do behind the curtain. See how everything is run here. So let's see. David Levy is not here. Uh, so let's say do some astronomy in the news. I don't have a whole lot today. My exoplanet report is we have 5,759 confirmed, up a few, and 7,217 candidates, up a few. And yesterday, I took part in a meeting with the Vatican Observatory Foundation and Brother Guy. He had a woman that he works with at the IAU there, and she is studying exoplanet spectra using the James Webb Space Telescope. So that was a very interesting talk. I swear, with you guys and the Vatican Observatory Foundation and all my friends in science fiction, I know the coolest people.
Oh,
I swear.
see the boot 2 nights ago?
Yes, I did. I go on a bike ride every night. So yeah, I'm aware of what's going on with the moon. Okay, so there is a space.com article. I mentioned Jim Shedlowski talked about this last year, and I mentioned this a little earlier, but space.com today posted radio pollution from SpaceX's new Starlink satellites poses threat to astronomy. And the article says that their new Starlink satellites produce 32 times more radio noise than their predecessor. And it's a real good thing for them that no one really owns space, right? It's like the wild, wild west up there. So, with that, I would say we all own space. Every human on the planet owns space, and it's not Elon Musk's playground. Sorry. Well, okay. When astronomers first started complaining about this, and his response was it was for the greater good. Oh, did I get a little miffed at that? So, our sun has been very active for about the better part of a year now. And let's see, spaceweather.com posted today another X flare might be in the offing. Sunspot AR 3825 has already produced two X flares. X 1.3 on September 12th and X 4.5 on the 14th. A third could be in the offing. Sunspot has a Delta class magnetic field that harbors energy for additional X class explosions. So, chance for more aurora. Keep your eye out. Okay, so let's see. Observing reports. Charlie, let's show your moon picture.
All right.
I will show your moon. Charlie took a picture with his sea star. Where's my mouse? And he wants to show it and ask a question about what is this. So I will share that. And you guys can't see that, so it needs to move over here. All right, can our viewing audience see the moon?
Yeah.
Dale? And you guys see
we're
that?
seeing it.
Okay.
We're seeing it.
This is a picture that Charlie took. He wants to know what that yellow circled thing is. That whole region. Any idea? I told him we'd have to hit up the Astronomical League's observing crew, but or ask Rick Hill. So if anybody knows what that is, or if anybody has a guide,
Yeah.
that would be good.
I noticed it's got some sheer pipe walls straight up and down. If you see by the fine edge there in the deep shadow. So, it could almost look like a building of some sort. Look at the shape of it. It could be an adobe building.
Really big building.
Missing.
It's all
Anybody else have any observing reports?
there for.
Anybody see anything in the sky interesting lately?
Yellow circle.
Yeah.
Oh, yeah. Anybody see the eclipse? I did not actually see that. Wow, about half of our audience. Okay, I feel bad. I should have seen it.
It was just the earth's shadow.
Yeah, it was just a small bite, wasn't it?
Bob, I got some photos to share if that's an observing report.
Yeah, go ahead, Dale.
Okay.
He's up on there, yes.
Sure. So here's my obligatory moon eclipse photo. Can you see that?
Yes.
Okay. I almost missed it. I was like, set my timer. My wife was working till like 10 o'clock and we were having dinner. It's like, oh, wait a minute. The eclipse is going on. I need to rush outside to grab a photo.
Hey, Charlie, did you see that
Yes.
comment? We got a comment. We got a comment in the chat that answered your question.
Oh, good. I'd like to know more about that.
Here is a photo of the elephant trunk. I took this with my Sea Star. This is 12 hours worth of data. So this is the most I've ever gotten out of a Sea Star photo.
Is that one night or is that several nights?
That's 4 or 5 nights maybe worth. That's a lot. It was too much for the internal memory of the Sea Star. Took me longer to process that than normal. It's that out of memory. It's like 5,000 subframes. Here's Cocoon Nebula. This is 163 minutes. That's with the Sea Star.
Wow.
Yeah, I haven't done a while, and then I processed some stuff. My only planetary photo from this year so far, Saturn, during opposition.
Yeah, those rings are getting real thin.
They
When
are.
is was it next spring they're going to be at equinox?
March, I think.
March.
So there's 5 moons. I always like to get the moons when I'm doing that. We got Tethys, Dione, Titan, Enceladus, and Rhea, I believe. And my last big one here. This is 18 hours worth of data on the Cygnus loop here. We got the Veil Nebula. So I've done parts of this before, but this is the most I've done. This is a 100 megapixel photo. So there's a lot of data here.
That looks great, Dale.
That's pretty.
Yeah.
Wow.
Lots of data. So this is I took almost 30 hours and I discarded quite a bit because of the wildfire smoke, but I kept 18 hours worth. It's pretty
Dale.
Cameras that with?
Huh?
What was that? What'd you take that camera with?
This was not with the Sea Star. This was
I
with
understand. That's what I'm asking.
my little red cat, which I showed a photo in that the one I had to the observatory, the Stargate. That little portable rig.
Right.
Did that. So
Thank you. That's very cool.
20-pound telescope.
Good job.
Anybody else have any pictures? All righty. So let's see. What's next? I'm glad I have this here. Oh. All right. So we're a little bit early, but that's fine. We'll take a snack break now and we will reconvene in 20 minutes, which will put us at 20 minutes to. So take a break. Be back in 20 minutes.
I gotta see this comment here.
You see that? Oh, there's I'm gonna have a picture of the eclipse on Flickr here, so I will share that too. Oops, opened up in my other window.
Oh, there's an answer. Part of the moon. Somebody being a smart ass. Right out there, smart ass. Yes.
Here. There we go.
Okay.
Invite taken out. Very cool.
Oh, you're manning the table. I did not copy these. These were the downloads off the website. This is what she sent us. Which there's not much there. So what I did was I copied off the original because they make the clearest copies. So I did not do this. Those are original PDFs that I downloaded, but I did not copy them. I have a feeling that those are basically these, but updated. And those are easier to download and print, whereas these are not. So,
I like that.
yeah, but I think that one is,
Hey, don't get in trouble doing it.
it's on the back side of the scrap paper, you know, during black. Yeah. Myself, you know, it's ridiculous because it's unnecessary and they're really wasteful over there. So what I started to do was print out on the backs and now it's a game.
Okay, we've got our audience here who wanted to share this with people. This is very There's a lot of light. Yeah, there's way too much. There we go.
The letters, whatever. They will make it.
There we go. All right, so there we go. It's better. Better. There. Trying to get it right here. Hail Bob. Too much light in this room. That's better.
Bedlands, dark sky bar.
Upside down.
I do.
Going that way.
I find,
Signed by the photographer.
John. John Children.
0.5.
Very cool.
Pretty good point.
Are you doing? Presentation at St. Isaac Joe next Friday for Bob Berta?
Next Friday, did I get email from him?
Yeah, you did. Cause I said I'd bring my telescope.
Let's take it around and show it to people.
This is our 9/11. My telescope.
That's cool.
Isn't that beautiful?
That's very cool.
Time we were just talking about.
It was hard.
Oh, were you holding it?
Yeah, that's tough to do.
You gotta get yourself, they have these little iPhone mounts.
I bet.
Hold it nice and tight.
Where they, so they actually have a phone mount. Where you just it clamps into it, then the eyepiece goes right here, so that way when you put it in there, it's already centered. Then all you have to do is focus and just go beep, beep. I have one from Celestron, has the Bluetooth trigger. So once I get it in there, it'll without touching the phone. That was a very good. That's nice. That's, look at that. That's a, you see that one right there? Look at that. That's a nebula. Check with Bob today. I'm gonna be there with telescope.
I think I can, but,
What's you just let Bob know.
I need to, what I need to do is I wanted to make sure that Jeff got that. We had put a message out to the membership. If even wanted to.
So he was, he asked me, I said, so I could do. Like, we could bring my computer and do like, show some slides or something, but I would need a projector.
I've got a lot of projector.
Okay, well, that's, let's run it by Bob. See what
He's online.
Okay, well, like I said, I sent him an email just to make sure that we get this thing working. So if I gotta pick it up for some reason, Oh, I don't know what the church has.
Where is it?
It's in St. Louis Shore somewhere.
I got it.
Yeah. Harper.
Number, but yeah. It's just. All right.
I'll talk to you this week. And I'll be there. Right, yeah, a whole bunch of. Yeah. I made a solar filter for the 22 inch. Like, the mic's got to it and start chewing on this foam. It's like the foam board. So I bought the new foam board, doubled it up. And it's now the office. So I had that done about 6-7 years by, so anyway, it's nice. And I named the cover like for like less. So let's go on. So we're out, we got, so it's good to get there. So you can see the telescope. Sure. Yeah. Yeah. There's something going on with done, you know. So, yeah.
Here I am chatting with people around here, and we're 2 minutes out from the start. One-minute warning. Messages here. Get the presenter view here.
Intrigued by this stuff. It's just a big open today. I will. Is how there we go.
Okay, can everybody online see that okay?
Okay.
Yeah, I see.
Good. All right. Here goes. All right. We're get this started. Can you blow it again? Thank you. The Thunder. Okay, welcome back, everyone. Our feature talk tonight is Dr. Rajib Ganguly. Did I get that right?
Yep.
Okay, awesome. He's an associate professor in the Department of Applied and Engineering Physics within the College of Innovation and Technology at the University of Michigan-Flint. He also serves, I should really be doing this. Yeah. He also serves as the Director of General Education for all UM-Flint. His research interests include astrophysics, supermassive black holes, quasars, and quasar outflows. His talk tonight is The Universe Through Superman's Eyes. Let's give him a big round of applause. Welcome. All right. I'm going to mute my end here and take it away.
All right. Thank you for inviting me to give this talk. My first memory of seeing a movie is waking up in my parents' car at a drive-in theater as they were watching the end of some movie that I can't remember. It was a double feature for which they only planned on watching the first movie and then taking off for the second one. Unfortunately, since I'd woken up at that time and I saw what the second movie was going to be, I wouldn't let them leave. At least that's the story that they tell. That movie was Christopher Reeve's first outing as Superman. Since then, Superman has always been my favorite superhero. Now, I should certainly acknowledge that Supergirl has all the same abilities as Superman. So in all fairness, I should retitle this the universe through Kryptonian eyes. You're welcome. All right. So one thing that amazed me from childhood about Kryptonians was that they could see things that we could not. As my interest in astronomy grew, I learned that we humans could invent different types of detectors and telescopes to see across the entire spectrum of light, from the radio to the infrared, to the visible rainbow, to the ultraviolet light, X-rays, and gamma rays. These new technologies have opened up the universe to us in ways that we never expected. So a question that simmered in my head was, how do Kryptonians actually see the universe? Let's put some things in perspective and define what it is that we can see and what Kryptonians can see. To start, here's a standard piano keyboard. I'm going to take that as a representation of the range of sound pitches that we are able to hear, roughly 8 octaves-ish. By comparison, the range of pitch or frequencies of light that we can see is essentially just 1 octave. Kryptonians, on the other hand, are capable of seeing more. They have X-ray vision. They also have this thing called heat vision, but they don't collect information about their environment for that. They just use it to zap things. So I'm not going to consider that. X-rays are much higher pitched than visible light and a lot more energetic. X-rays were officially recognized in a paper by Wilhelm Röntgen in December 1895. Among his first subjects investigating the properties of this new type of radiation was his wife's hand. On seeing the first medical use of X-rays, his wife reportedly said, "I have seen my death." I am sure we're all aware of the wide use of X-rays in the medical field and even airport security. For his efforts, Röntgen received the very first Nobel Prize in Physics in 1901. Superman, by the way, first appeared in the first issue of Action Comics 37 years later in April 1938, a few months before my father's birthday. I'm not sure if that's a coincidence. Returning to the piano analogy, Kryptonians surely see what we see in the visible range. At higher pitches than visible light is ultraviolet light. I'm not aware of Kryptonians having ultraviolet vision, so there's a gap in what they see. In order to put X-rays on this piano, I have to add many, many, many more octaves. X-rays start roughly 9 octaves higher than what we can see and span roughly 13 octaves above that. Now, what are the technologies that let us see what Kryptonians see? Here we have a problem. Shown here is a diagram of how opaque our atmosphere is to different wavelengths of light. You can see that visible light is in this nice sweet spot here, where light from the sun can make it to the ground. At smaller wavelengths, or higher pitches, atoms tend to absorb that light. This is a good thing for us as it protects us from potentially hazardous doses of ultraviolet radiation. But the atmosphere also blocks X-rays and gamma rays. This is also a good thing that we don't all turn into the Incredible Hulk, but that's another talk. Sorry. Incidentally, at wavelengths longer than visible light, in the infrared and microwaves, molecules in the atmosphere are able to absorb light through vibrations and rotations of the molecules. A large swath of radio waves do get through unimpeded, but there are fundamental reasons why we didn't evolve eyes that could detect them. Our eyes are too small to be able to make use of radio. I'm not aware of Kryptonians being able to see there either, as they would have the same issues. As such, the first answer to my question of what do Kryptonians see when they look up at the sky is rather uninteresting. They see exactly the same thing we do, since that's what Earth's atmosphere lets them see. But Kryptonians can fly, and they can fly above the atmosphere where they have access to the X-rays. So to see what they are able to see from up there, we have to go to space. And that brings me to the first example of showing you what Kryptonians can see. And that is the source of their power, the sun. In December of 1995, the Solar and Heliospheric Observatory, or SOHO, was launched with the capability of detecting X-rays from the sun. Speaking of super things, SOHO had its 25th birthday in 2020, the COVID year, which means it is currently in the 29th year of operation out of its 2-year projected lifetime. It has observed 2 complete solar cycles and given us many interesting results. Now, this is how you would see the sun if you looked at it safely. But let me be clear, you should never, ever do this. If you must, use a digital camera and point it at the sun and look at the screen. It looks rather plain. However, if you have a digital camera, and I suspect many of you do, you can put it on the business end of a telescope and put a filter on front to see this. This is how the sun looks in one particular wavelength of light, of visible light, at 656 nanometers. This is called an H-alpha image, since the light there is coming from a particular transition in hydrogen. You can see that there's interesting things happening. The bright thing right here is the region between 2 sunspots that we just talked about before the break. You can also see some prominence here at sort of the 10 o'clock position up here. Okay. I put this here for reference. SOHO observes the sun in X-rays and the extreme ultraviolet. Since X-rays sample a large range of pitches, SOHO observes at 4 individual wavelengths. Here are some movies with some of those observations. Hopefully the moves are coming through. Yeah. These are false color, progressing from blue to green to yellow and to red. The wavelength is increasing, pitch is decreasing, so blue is the highest energy X-rays. From these observations, we see that the sun is not a featureless and static thing. It is very dynamic, with coronal mass ejections, sunspots, and twisting magnetic fields. As we have already noted, SOHO has been taking data through 2 solar cycles. In the visible range, we see the cycle in terms of sunspots, which get larger and smaller in number with a periodicity of 11 years. We can see here that this also correlates with the activity of the dynamic sun. As the number of sunspots increased from 1996 to 2001 and 2002, the high energy light becomes more and more prevalent. And then it ebbs again from 2002 to 2009, only to rise and fall again. From the combination of X-ray and visible light, we can see that the sunspots are the base of these twisting magnetic field lines, where magnetic pressure is able to provide added support against gravity, allowing this gas to cool and become darker. That's why it's a spot. That brings me to another example, which is a little more personal. I was a graduate student at Penn State from 1996 to 2002. During that time, NASA was in the midst of its Great Observatories program that saw the launch of Hubble, and Spitzer, and Fermi. We're going to watch a video here of the launch of another great observatory in July of 1999. Pay attention to the announcement at the end of the countdown as the Space Shuttle Columbia takes off 38 seconds into the video.
25 seconds.
T-minus 20 seconds. 15 15, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. We have a go for engine start, 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Columbia is in the roll.
The announcer says, reaching new heights for women and X-ray astronomy. Let me take a brief aside regarding that statement. It was in reference to Colonel Eileen Collins, who, with that launch, became the first woman to command a shuttle mission. She had also previously become the first woman to pilot a shuttle, and later, when Columbia broke apart on re-entry in February 2003, resulting in the grounding of the shuttle pending investigation, she also became the astronaut that finally took us back to space aboard the shuttle Discovery on a mission SES-114 in 2005. She certainly makes a strong case for being called a real-life superhero. But back to X-rays. The great observatory that was launched in July of 1999 was the Chandra X-ray Observatory, shown here. At Penn State, Professor Gordon Garmeyer was the principal investigator in charge of designing and building the Advanced CCD Imaging Spectrometer. As the PI, he was guaranteed a certain amount of time to do science with his instrument. So we were really interested in seeing a successful launch and eager to see this instrument in action. Interestingly, the launch was actually the third attempt after 2 scrubs due to weather, and we were on pins and needles at the time. Anyway, I want to show you a really interesting feature of how Chandra works that lets us see what Kryptonians see. The design of a mirror assembly made by Eastman Kodak. This is a close-up of one of the mirrors used by Chandra before the reflective coating was put on. Notice that it doesn't look like a normal mirror that you would put on a telescope. There's a giant hole in the middle. This is by design. When X-rays hit a normal telescope mirror, they just get absorbed. They don't get reflected. Instead, one has to angle the mirror to the extreme to let the X-rays graze the surface and change its direction slightly. This greatly affects the effective collecting area of the telescope. So Chandra's trick is to nest 8 of these highly angled mirrors so they all have the same focal. So what's the result of this odd mirror design? Well, here's a Hubble image of the Type 2 supernova remnant Cassiopeia A. The name indicates that this is the brightest radio source in Cassiopeia. A Type 2 remnant is what's left over when a massive star blows up from trying to fuse iron in its core to support itself against gravity. With a Type 2 remnant, we expect there to be a dense core that is left over with all the blown off outer layers, resulting in the beautiful nebula that you see here. But where is that core? We can't see it. Here's what Chandra sees. Kryptonians can. It's right there. Plain as day in the X-rays. That's a neutron star that's emitting the X-rays. That's really cool that they can see that. How about another example? This is the Hubble view of what the Crab Nebula looks like. Of course, when you look at it with a normal telescope, it actually looks kind of like a crab. But as usual, Hubble just completely destroys that with its incredible resolution. Still can't see the leftover remnant of the explosion, though. This is what it looks like in X-rays. There is the neutron star plain as day. Remember, of course, that Kryptonians see both visible light and X-rays. So I imagine they see the Crab Nebula, something like this composite. It's really cool to see that there's this cavity formed by the visible light image, and that cavity is filled by the X-rays, indicating the gas there is extremely hot. But wait, there's more. Take a look at that ring of gas around the neutron star, right in there. Chandra has gone back and observed it a number of times. This is a sequence of images from September 2010 to April of the following year. You can see the development of bright knots in the ring, indicating the impact of a shock wave over here in the ring. We've also seen this kind of feature in monitoring of supernova 1987A in the Large Magellanic Cloud. So, from the remnants of stellar death, we head to the other extreme, their birth. Here we see the Orion constellation. We zoom in toward the scabbard, where lives the Orion Nebula. As we get closer, we see an optical image, and closer still, a Hubble image comes into view. As we get closer, the Hubble image will morph into what Kryptonians can see, what Chandra sees, like that. With visible light, we really only get a glimpse of what is happening. In the X-rays, we see much more in terms of the stars. The nebula is largely invisible to X-rays, and they come to us unimpeded. As I blink these two pictures, take a look at the marked differences. You can certainly see stars from the Hubble image. Take a look at those three, for example. They're right there. But the Chandra image shows much more. Notice that this star up here, this blue star right up here in the Chandra image, it's not there in the Hubble image, hidden from view. Well, enough about stars. Let's turn our attention to galaxies, starting with our own, the Milky Way. This is a very wide-angle visible light image looking at the center of the galaxy. A screenshot from Stellarium is shown in the top left, with constellations drawn to orient you. Antares, the bright star in Scorpius, is here. Since we live in the disk of the spiral galaxy, our insider's view looking toward the galactic center features a bright stripe of stars, which is the rest of the disk. The stripe is, of course, the origin of the term Milky Way. In the visible light image, we also see shadows from large lanes of dust, which obscure our view of what is on the other side. Zooming into the central region, we find a star field that seems like any other field. Keep in mind that the stars in this image are ones close enough not to be obscured by dust. As with the Orion Nebula, X-rays give us an unobscured view. There are lots of individual bright X-ray sources, and I want to highlight two of them. The first is a source known as the Great Annihilator. This is the brightest source in the sky at 511 kilo electron volts. That's an energy, the energy that corresponds to the mass of an electron, courtesy of E equals mc squared. This is a result of electrons and the antiparticle electrons, positrons, annihilating each other. The source itself is known as an X-ray binary or a microquasar and involves a black hole and a companion star in orbit around each other. As they dance, the side of the companion star that is closer to the black hole feels a stronger gravity from the black hole than the star itself. So gas from the star is slowly siphoned off and accreted onto the black hole. The other thing to highlight in this image is the center of the galaxy and the source called Sagittarius A, the brightest radio source in the constellation of Sagittarius. The X-rays reveal incredibly hot gas in this region, where lives a black hole, as we know, of incredible mass. There's the EHT image. Thanks, EHT, for giving us that. Several hundreds to thousands of times more massive than the sun. Speaking of supermassive black holes, that's my bread and butter. Here's an oddly shaped galaxy designated NGC 6240. The irregular shape is an indication that this is the result of two galaxies having collided with each other. Here's an X-ray image of the central part of this galaxy. Since the X-rays can pass through the gas and dust unimpeded, we can see the images of two black holes from the two parent galaxies that merged. The black holes have sunk to the center and will eventually merge as also. And eventually we'll get gravity waves from it. This is an important component in telling the story of how the universe changes over time and how gravity drives the establishment of structures, how galaxies evolve, and how black holes grow. Another interesting part of that story is the part told by this galaxy, designated NGC 1275 in this Hubble image. It is also known as Perseus A, i.e. the brightest radio source in Perseus. Black holes can grow in basically two ways, As we've already seen, they can merge with other black holes, or they can slowly accrete matter. Slowly, in the context of a supermassive black hole, is about 1 sun per year. This is what the black hole at the center of NGC 1275 is doing. And the effect of that feeding frenzy is pretty messy. Here's a cutout and zoom in on that galaxy. It looks like a monster with tentacles, possibly something a Kryptonian would have to protect us from. The process of feeding the black hole at the center of NGC 1275 is messy. It results in a lot of matter actually being driven away, blowing out the galaxy's gas. NGC 1275 is part of a cluster of galaxies, and the blowout has an effect on the hot gas that lives between the galaxies in the cluster. We can see this in X-rays. The X-ray image reveals how violent this feeding black hole is. You can see bubbles and shocks. These can be enhanced through some processing, as shown here, to help guide the eye. And furthermore, here's an animation showing a source there with jets that are going to come out, and it's going to impact the gas around it and show us these bubbles to show us what and help us interpret what we're looking at. Okay? So that's showing the development of concentric ripples from the impact of a jet, which is reminiscent of these observations. But of course, Kryptonians see both. So it behooves us to combine them to see what they see. This is how they perceive the monster. In the final part of our tour of the universe as seen by Kryptonians, I've pondered whether they can see dark matter. While we haven't identified dark matter yet, we have inferred its existence and know an important property. Its interaction through the electromagnetic force is somewhere between meh and no. As such, it does not interact with light. Hence, it is dark to us. It also does not push or pull, because we need the electromagnetic force to do that, or crash into things like normal matter. But it does have mass, and therefore, according to the laws of general relativity, it is able to deform space-time. My favorite example of dark matter is one using what is called a gravitational lens. Suppose you have a cluster of galaxies that lies between us and a more distant galaxy, so that the warping of space around the cluster can bend light from that galaxy toward us, in a similar manner that a lens can change the direction of light from an object and focus. Of course, the galaxies in the foreground cluster don't typically or magically align themselves to give us a high-quality lens, so the images tend to be like this. The background galaxy tends to be distorted as seen by the arcs in this image. Let me see if I can point out a couple of the arcs. So here's an arc right here. Here's another one right here. All these are distorted images. There's one up there. There's one over there. Another one over down here. They're pretty much all around. So suppose you have a cluster that lies between us and a more distant galaxy. I already said all that. Let's see. Yes. So keep that in mind as we consider this image of what is called the bullet cluster. This is a nice Hubble image of the cluster, and one can see the galaxies. You can also see a star in our own galaxy. It's the bright spot with the crosshairs, right? If your eyes are better than mine, you can probably also make out some distorted galaxy shapes that are a result of this lensing effect. In X-rays, clusters look very different. X-rays show us where the hot gas in the cluster between the galaxies lies. And in the X-ray image of this cluster, overlaid on the Hubble image, shows us why it has the name bullet cluster. It is actually two different clusters that are passing through each other. And you can see a bow shock that's very reminiscent of a bullet going through some medium like this. There it is. This image shows us where the matter that interacts with light lives. But gravitational lensing tells a different story. We can use the way in which background galaxies are distorted to map out where the matter is that is deforming space. And that matter is here, overlaid in blue. It doesn't match where the normal matter is, which throws out a very important challenge, I think, for any alternative theory of gravity that's trying to not invoke dark matter. Surely, Kryptonians can see this. So I wonder if their brains had evolved to be able to map out this in their heads before Krypton met its demise. I'm not sure. X-rays reveal to us a universe that is a very dynamic place. Kryptonians are able to see much more of the universe with their naked eyes than we can. But we have technology that lets us see what they see and more. In order to construct the complete story of the universe, we have to look beyond what just our eyes show us. Thank you.
Alrighty, do we have any questions for our presenter? No? I have a question. Yes, go ahead.
If it even makes sense, but would it be possible theoretically to vision through neutrinos to have some sensor that could do similar kinds of things like with the X-ray?
So one of the big things actually nowadays in astronomy is what's called multi-messenger astronomy. So we get most of our information through light. We're starting to get information through gravity waves. So that's another kind of messenger of information. But we can also get particles. So we get cosmic rays. Neutrinos are also another thing. I mean, I think technologically we're still a ways off from being able to really use neutrinos as a means to sort of image things. But I'm not going to put it past us in the far future being able to do that.
Okay, thank you.
I have a question for you about those the colliding galaxies with the two black holes that are going to merge.
Right.
Is it going to create a gamma ray burst that's going to sterilize those galaxies?
No, there's no so the gamma ray burst often results in the formation of a black hole, a stellar mass black hole. These are black holes that are much bigger than that. So that's ancient history for these guys. The idea of gamma ray bursts. Yep. We will get bursts of gravity waves once they get close enough to actually merge. And that'll be super exciting.
In a few million years.
If that.
Yeah, well.
I probably won't be around then.
Any other questions? All right. Well, let's thank our presenter again. And
Dr. Ganguly, I have a question for you.
Yeah.
So what do you got?
So the Chandra Observatory has been up there for quite some time. Do they have the next X-ray type one planned on the boards?
There have been many plans. None of them have actually made it through the development stages to actually be constructed. So we're going to have a gap. I mean, Chandra is actually being turned off, as it were. That's a travesty, in my opinion. But yeah, we're going to have a gap in our capabilities in the X-ray. We already have a gap in our capabilities in the UV. Once Hubble goes, UV is completely gone from us. So we have.
What about New Star?
I mean, New Star is there. XMM is still there. In terms of high quality imaging, though, Chandra was really the name of the game. Yeah. So XMM and New Star were really good for doing spectroscopy. because they're basically light buckets. A New Star was really good for doing high energy stuff. Yep. Or is, I shouldn't say was. New Star is still in the present tense.
Okay, so any other questions? All right, so closing here, astronomy at the beach tomorrow. I'll be there or be square. Very cool event. Our next star party and open house at Stargate will be Saturday, September 28th. Our next board meeting is the 30th. Our next general meeting is October 7th at Cranbrook. And after this meeting, we're going to meet at, some of us go to the National Coney Island on Groesbeck and 12 Mile. And with that, we're done. Clear skies, everyone. Good night.
All right.
Righty. Microphone. Take me an hour and a half to close down now. Hello.